elongated surface. So what we're looking at here is what drives plate motion. So Earth's surface is made up of 8 major plates, 10 minor plates, and dozens of microplates. In Activity 1, you saw GPS data that indicated plates are moving in different directions and at different speeds. So what causes these plates to move? Let's take a look at this animation. From 200 million years ago to present day. So this is pretty much when I was in high school until today. You can read the bottom. It's talking about where things were located 200 million years ago. The Atlantic Ocean started to open up around that time. Beginning in the north, tectonic plates were moved apart, and new crust formed in between. We can speed up time so that millions of years flash by every second. And this change in tempo will allow us to witness geologic time from our impatient human perspective. Europe, North America, and Africa split apart first. And as the southern Atlantic opens up and Africa and South America drift apart. The underwater ridge that traces the center of the Atlantic Ocean reveals the location of new crust forming. The youngest sections of the ocean floor lie near the ridge, with older, cooler, denser crust near the shorelines. The process seems smooth and stately from this perspective, but most of the plate's motion takes place in a series of adjustments we call earthquakes. Sometimes minute, sometimes minute, sometimes whatever that said. These events shaped the landscape we recognize today. And that's to present day. So, do you remember this question? Where is the youngest crust? And what do you think might be causing Earth's plates to move? We're going to move on to the next part. New thinking on how Earth's plates move. As scientists gather more data and evidence, they continue to improve their explanation of how the world works. Current models of plate motion have plates moving as part of a gravity-driven convection system. What does that mean? This video will describe that. I'm tentative about showing the video on WeVideo because you get some issues with audio, so I will show that in class. From the video, at which type of boundary does ridge push occur? At which type of boundary does slab pull occur? How does gravity cause plates to move? And then it has you explain your answer, which we will not do. Question 7 says, at the mid-ocean ridge, the tectonic plate is about 32 kilometers thick. As the plate is pushed away from the mid-ocean ridge, it gets thicker, up to 100 kilometers thick. Why does the plate get thicker as it ages? Why do you think? And then question 8 says, why do earthquakes happen only in the brittle crust and upper mantle? How are plates moving? This says in the Tectonic Explorer model, you can see new plate material being formed at a divergent boundary and old plate material going back into the mantle at a convergent boundary. Is there some connection between plate boundaries and the forces driving plate movement? Let's use Tectonic Explorer to investigate. The Tectonic Explorer model is already set with the cross section. When you start the model, you will see that the center of each plate on the globe is labeled with a number. You may have to rotate the planet to see the number on each plate. Run the model so you can see what's happening with plate boundaries. So I'm going to go ahead and run this. Start. Okay. You should see this plate being subducted beneath the continental plate. Remember, this is oceanic plate. This is a mid-ocean ridge. And so that's what's being shown in this cross section. You have a mid-ocean ridge underwater here and an oceanic plate being subducted under a continental plate. Here you can see a key on the side, elevation, and it shows you what color continental crust is, what color oceanic crust is, which is the dark blue. The lithosphere is gray, and the mantle is green. Question 9 would have you answer this. There are 3 different plates visible in the cross-section. Draw arrows between the planet view and the cross-section view to show how the plates in the cross-section view match up with the planet view. If that makes sense to you, we're looking at, there's an oceanic plate here, and that would relate to this area. There's an oceanic plate here, and that relates to inside here. And this continental plate is right here, that other plate. You have, hopefully you're able to determine those 3 different plates. Okay, finally, solving the mystery of how plates move. This is the important part. It says, as you learned in the video on page 2, scientists have changed their explanation of what drives plate motion over the years. The study of plate tectonics is a young science, and there's still much to learn. How did scientists come to the conclusion that mantle convection is complicated, as shown in the diagram below? Like many advances in scientific fields, technology played a role in scientists' better understanding of what happens inside the Earth. Scientists are now able to see into Earth's interior by using a tool called seismic tomography. As earthquakes happen, scientists can determine how the waves move through different portions of the planet. Earthquake waves move quickly through cold rock and slow down when moving through hotter rock. Using computers, scientists can translate the speeds of seismic waves into temperatures and make a 3D model of Earth's interior. The image below shows a model of it. It says that a tectonic plate sinking under the United States. So here's the United States. And you have a subducted plate. So it says this actual seismic tomography image shows a cross-section of the crust and mantle underneath North America. Blue and green shades mean colder and stiffer rock. Okay, you can see some blue and green. And red shades mean warmer and weaker regions. Scientists think that the 3 here, green diagonal shape, and the green and blue above it and to the west are the remnants of an old tectonic plate that has been subducted underneath the North American plate. It was ocean seafloor off the coast of California more than 30 million years ago. This plate is responsible for the formation of mountains and ancient volcanoes across much of the western United States. The image shows that now the remnants of the plate are still sliding to the east and sinking further into the mantle. Currently, the bottom of the plate is deep under the east coast of the Atlantic Ocean. Okay, so these are what formed like the Rocky Mountains and things like that, that old subduction area there. How does the seismic tomographic image help to confirm what is happening beneath Earth's surface? Well, we don't need to answer that right now. And that is it for this activity, everybody. What I'd like you to understand from it, though, is the convection currents. You'll remember we did a ed puzzle on convection, the idea that mantle materials being heated moves toward the surface, moves across, and then sinks when it gets cooler, and that process drives the plates.